So, right. I do like XKCD has sort of an on-theme comic for most of our topics without too much stretch. So yes, we will still be talking about regression and curve fitting. And the reason for spending yet another lecture on it will hopefully soon be clear. Before that, there's a couple of announcements. As you guys all saw, assignment 1 is out. We'll talk about it in one of the future lecture sessions. Today, I feel like there's a fair bit of a material. And we will also let the questions and updates on assignment 1 settle a bit on Piazza before talking about it. Maybe Wednesday, maybe early next week. As you will also see that we are going to be covering a few things that you will be needing for the assignment, such as, well, we covered maximum likelihood estimation. On Wednesday, hopefully we plan to talk about KL divergence, which you will need. And then on Wednesday, we'll also talk about the Bayesian version of regression, which you will also need. And in, I believe, week 4, we'll talk about EM. Right, so there's that. On the course logistics front, we have onboarded 3 new tutors. All of them have taken the course last year, so they have lots of fresh memories to share. So they are Barclay, Ivan, and Zhiyuan. You can space yeah, on the website. Is someone not unmuted, or is it me? Tutorials already started this week. Great. I know that the tutorial capacity is basically tight, and so bear with us for those of you who have requested special attention. So Shidi Li is the dedicated tutor who will take care of all of these requests and get people into Watto. So just imagine if he gets 30 requests, it takes a while to sort things out. I will also basically add that the overall objective of all of us as a team, basically lecturers, tutors, and the 300 of you guys over the semester for the SML class is hopefully maximize our learning collectively. On your end and on our end as well. So we achieve growth through teaching you as well. And then while minimizing suffering, as a class, as large as this, there will be multiple coordination problems. There is a challenge of you guys learning with each other or asking us questions. So we have provisioned hopefully enough tutors to help you guys, but sometimes it does take things a bit of time to sort things through. Right, so do get in touch, preferably via Piazza, and we will help you. And lastly, I hope everyone is doing okay, given the COVID situation on campus and everywhere else. I know a lot of people are in isolation one way or another, and I hope they can make use of the online sessions and tutorials. So I hope we get through this stretch and hopefully life will be close to normal. So this is what we are really going to talk about today. The first part is, I would say, a slow restart on linear models. And then there are basically a bit of technical content on maximum likelihood, the geometric intuition on the solution, and how we regularize these squares. So with the multiple outputs, you can basically see the book. It's a simple intuition. And And then there's another bit of technical material on bias variance decomposition, which we'll cover. It also relates to the new generalization lecture that we developed for this year. And at the end, so as bonus material for this year, or new material, we talk about a modern development. Well, we call it interpretable and sparse linear models. This is also to tell you that not only is linear models not going out of fashion in the age of deep learning, but it has a lot of renewed energy and also impact, as we will see. So the first bit and the last bit were, I would say, a bit juicy. The middle bit are a bit dry, but bear with us. And these slides have been updated on Piazza shortly before the lecture. So if you want to download a new copy, go there and click. So the general motivation for linear models is why. Why? Well, the short answer is that saves lives. And it's, well, moreover, it's simple to apply. And it's easy to encode intuitions. Last year I chose this particular example since I started returned to teaching shortly after my son was born. So I learned about this Apgar score, which is a linear model that encodes 5 different factors. Hearing someone typing, could people please mute their microphone? Thank you, that's very good. Right, so these 5 factors have acronyms, and then they're used to judge, basically, after a baby is born, new to the world, after 1 minute and 5 minutes, whether their life is in danger. So you can imagine this is a linear model that's applied by humans, basically pediatricians and nurses. And it's been in use for a long time. And you can imagine for a person or for a medical practitioner within 1 minute and 5 minutes, where they're attending a lot of things happening in the delivery room, it is really a matter of life and death that they can correctly apply a linear model. This also appeals to the principle of Occam's razor, meaning the law of economy of parsimony of modeling. Basically, a model should be as simple as possible, but not simpler. This is what Albert Einstein says. So of 2 competing series, the simpler should be preferred if the quality of inference of the 2 are similar. To illustrate this, so the 5-factor simple factor Apgar score is also used to build modern, more up-to-date and more complex models for basically neonatal risk estimation. Right, so one example calculator online have many of these other factors. One of the factors is the Apgar score itself. Moreover, in Lancet, right, the top medical journal in 2003, there is this presentation of the CRIB score, a new one, also has a memorable acronym. But it was found that the risk indices are not so reliable anymore after a while, because when the indexes have been developed, it did not take into account the worldwide use of neonatal intensive care. Basically, because the medical profession have stepped up in taking care of newborns, the risk score sometimes overestimate the life and death or the risk of new babies, simply they have not, because the training data have not seen or have not taken into account that a lot of babies, at-risk babies, are being taken care of in NICUs these days. All right, enough of motivation. Hopefully you're somewhat convinced that linear models are useful for machines and humans to apply. And when we say linear models, we mean this. Yesterday we looked, well, actually last Wednesday we looked at the version where the prediction function is y, taking inputs x parameterized by vector w. And in particular, it looks like this. There's a W0, which is called a bias term. We'll address questions in a little bit, maybe after a while, all together. So let me know, pause for that right now. And then if there are K different, well, D different features, each of them has a weight W1 through WD that I learned. We can also talk about what's called a feature function version of it. Instead of, in addition to thinking about vector x as a d-dimensional vector x1 through xd itself, we can also put feature functions phi of x that does not have to be linear terms of x itself. So let's say in this particular case, there are m feature functions, and we can also write this as basically W transpose phi. So the top term, the top expression written in matrix terms will be W transpose X, but taking into account that this X vector essentially has a one term, like constant term in front, and then like the D components. So what's important for this slide is that the basis functions and the features are fixed and known. Right, so we basically have a parameter. We can write the basis function as a vector. The convention is also for phi of 0 to be 1. And of course, phi of 0 can also just be each of the features themselves plus the combinations. And W0 is commonly called the bias parameter. So why do we do this? So introducing feature functions. For those of you who have studied some versions of engineering or physics, you would know that, for example, sine and cosine functions are universal basis functions, in the sense that if we are allowed to have infinite number of these phi functions, like in real life, we just need, for example, the lower frequencies, sine and cosines, then we can represent most of the signals to a pretty good accuracy. But in theory, if we're allowed to have a countably infinite number of basis functions phi, then we can essentially approximate any continuous function of any input x on the real, like, d-dimensional space, which is nice. Despite the general nature of these phis, which we will comment on towards the end of either this lecture or the next about fixed basis functions. If we write the regression function in this linear form, we will have an analytic solution when we minimize the sum of the square errors, which is nice. Like neural networks don't have an analytic solution. Therefore, we're doing all the gradient descent, stochastic gradient descent business. But if linear algebra can give us a solution, then all the better in most cases. Right. And they also have well understood statistical behavior, where we can use these to reason about bias and variance, and can use this to motivate and design regularization strategies. So understanding these is quite crucial to the rest of this class, right? Moreover, if we are operating in a sum of square errors realm, efficiency algorithm exists for this convex loss. So for those of you who have not seen convex optimization or seen convex functions elsewhere, so quadratic functions such as sum of square laws look nice. Like you all know what one-dimensional quadratic curve looks like. So it looks like a ball with a unique minimum. So therefore, these loss functions are nicely behaved, and we can find the unique minimum, which cannot be said for many other more complex models. All right, so the convention here that we will adhere to for a while in this book is x's are the input, phi of x are feature functions on the input, right? Moreover, when we write, when the book says bolded capital X, it means a matrix like this, where the columns are input dimensions. Like, for example, this could be all ones, like it's all ones down here. And then from the last page, this is the first dimension, and the last one is x of d, the d's dimension, right? And then the rows are, let me check. Let me double check. This is still right. The rows are data points 1 through n. So what this says, it is a slightly like, it does require one step of transpose, right? So if I have input vectors that are called x1 through x big N, this matrix is basically a stacking of these vectors, but each of these vectors, like, there's also a convention in a lot of machine learning books. Well, if you read a paper, you should check, right? So a lot of times, input vectors or feature vectors are represented as column vectors, where x1 as a vector is actually a column vector, right? 1, 1 through x, 1d. And you first transpose that and then stack them into the matrix. These are worthwhile for noting if you're trying to derive some of these. Right, so for phi of x, the feature functions, so we could have polynomial feature functions. For example, this is linear, the green line is linear, the blue line is quadratic, and the higher order polynomials are like portrayed at the rest, where the even polynomials were these ball-shaped and the odd ones are these sort of wriggly shaped. Right? We can also have Gaussian shaped feature functions or sigmoid shaped, where the feature functions are essentially look like a generalized S. So without feature functions, we could only fit lines in high dimensions. With feature functions, we will be able to fit things like a sinusoid. As we saw in last Wednesday, with polynomials, we could fit the sinusoid fairly well, despite the sinusoid is not a polynomial. Here is basically the menu or a snapshot of the analytical form and graphical form of common basis functions. You can find it in the book. Besides the 3 that was mentioned on the last page, I won't read it out. If you need it, you can always look it up in the book. Right? There are Fourier bases, as we covered. If you've done engineering or Fourier transform, you know, like either the real or complex sines and cosines. Basically, they are valid basis functions. They are wavelets that are generalized upon Fourier basis to have improved space and time frequency. They are splines, basically piecewise polynomials. So these are generalizations of more complex, like simpler basis functions that we talked about before. That's enough for now, I think. So back to these two expressions of the predictor for the linear model. Let's look at how we do maximum likelihood estimation and least squares. So going back to what we said last Wednesday, we have the target variable equals to y, the prediction function plus noise. And we parameterize it with, we assume the noise is Gaussian, therefore the conditional distribution of the target given prediction is a Gaussian, centered around the prediction function, hopefully, and with precision parameter beta. Again, this picture we've seen is like a picture that will appear a few times. So if we compute the likelihood of this Gaussian likelihood function, basically, if we see a bunch of x's and t's, because it's regression, we assume the x's and t's are already drawn. We multiply this Gaussian probability together. We take the log. It breaks. Right. Then we can also break apart the log. Right. So let me address some of the follow-up questions. So the first question by Qinyu is components in the score are not in Rn, right? Observed continuous. They are not continuous. So so the input are given. The fact that a linear model is a linear combination of the input doesn't constrain the input to be strictly on the real line. And well, moreover, these are input generated by doctors, so integer inputs are actually okay. Moreover, if you're learning these from data using a computer, you can still do gradient descent or apply the normal equation, because the wave vector that we learn, well, with a computer without any constraints are still in the real life. Hopefully that's, and yes, it's still called a linear model because the prediction function is a linear function of the input or feature function. I hope that helps. Paul Wang asked, what's the E looking thing again? I'm not exactly sure where. Oh, you probably mean this term, the noise term, epsilon, eta. Okay, my Greek vector is a bit crappy at this moment. This is noise. Basically, the picture here is given the prediction function y on this y curve, this red curve on this particular value x1, x0, the target is not exactly on this prediction function. Otherwise, we don't have anything to learn. As if you remember from last Wednesday, a lot of you probably not, because you've had in lots of classes, the target are scattered around the prediction function, right? So the distribution for the target given the prediction function is assumed to have an additive Gaussian noise, IID as well. So there's that. I hope that was, yes, okay. Okay, yeah, we'll look at these terms a bit more. Right, so taking the log of the Gaussian distribution function expands into something like this. Let's just look at it slightly more closely. Again, the value of seeing these similar expressions a few times these few weeks will hopefully pay off. Right, so in this particular case, as we did on Wednesday, basically the sum of, we take the log of these product terms, we break break them apart and also incorporate the sum when it can be incorporated. So log of beta essentially, and log of 2 pi minus 2 pi because it's at the bottom. And these two are constant terms, therefore the angles in front. And then what we just did is we call this longish looking term inside the Gaussian the error term. And turns out that we can just basically decompose the likelihood function into these, one involving beta, the second term is constant no matter what, and the error term. So log of x cancels out each other. So therefore this error term is essentially 1/2, right? As reflected here, and we also like 1/2s in these square terms. They are essentially basically Tn minus the prediction function W transpose phi. So what did we just get? Right. So basically we started writing our likelihood term assuming Gaussian noise, and we get square error, essentially the sum of square error for each of the training data points, Tn and Xn. Right, so the claim that we essentially arrived at this page is maximizing the log of likelihood of training data is equivalent to minimizing this sum of error function. Okay, follow-up question, what is beta? I won't flip back and I will just explain it here. So beta term here, yes, it's what's called a precision parameter for Gaussian distributions. So it's the inverse of sigma squared. It's written as precision rather than standard deviation because of convenience, as we will see when we get to the vector or multidimensional Gaussian this Wednesday and the Bayesian estimates. I hope that helps. So in least squares, if you're solving for least, like solving linear regression using least squares, beta is not here, right? As you can see, equation 3.12. You don't need to care about beta at all. The benefit or what this probabilistic formulation buys us is that we can estimate beta. We can explicitly take beta into account. We talked about this last Wednesday on the expression of estimating the beta. I'm not going to repeat it here. You might have to do some lookup across the two sets of notes and book, like corresponding book parts, right? Right, so we've been like talking to you in these matrix and vector expression. So let's do that here. Also, you've seen the like scalar form a lot last Wednesday. So let's do a matrix form. So this is also a very common manipulation when you have a long L2 like square loss, sum over square loss over data points. You rewrite it as an inner product, actually a vector inner product. What this means for, I guess, a lot of, okay, I'm going to say that like I'm one of the mere mortals who cannot reasonably reason about matrix and vectors until a lot of practice have been had. So if you are someone who is like me, there are people for whom the matrix and like vector operation is completely intuitive. If that's the case, you can go make a cup of tea and come back. So this is vector t. And then we have basically the feature function phi or big X, which is shaped like this is dimension D or M as notated a few pages ago. And then it's basically m by d or m. And then the vector w is, let's say, because it's phi, let's, to avoid confusion, people who look at this, the vector w is of dimension m. Actually, I did this wrong. It's of dimension m, but this way around. So this is what basically the error term look like in matrix notation. Yeah, from linear algebra, the product of the latter two is basically n by 1 vector as well. And this is where the inner product come from, right? So, and the rest of the page pretty much says the same and expands the phi for us. So note that each row of 5 is also like a transpose of a column vector phi. So if we plug into the likelihood function we worked on the last page, the first two terms are the same. The last term is, we are just notating the square error in as a vector in the product, okay? What does this buy us? We just expand this expression. So the first line is the expression from the last page. Hopefully we convinced ourselves of it. And the second line just plugs the inner product into this and replace it with the error term. And now we take the vector gradient with respect to W, because we're trying to learn this weight vector W. And because this is a quadratic term involving W, right, we can be sure, and it's also, we know that this is quadratic term, sort of, yeah, with the both facing up. We can take the gradient, invoke our matrix cookbook, if we're not familiar with this. A lot of times you could try and understand the results from the matrix cookbook, pretending these vectors and matrices are scalars. In this case, we know, oh, this is a quadratic term involving W, so therefore it must like have a 2 in front, indeed, right? The constant beta is preserved. And then it's a quadratic term of a linear function of W, therefore the phi comes out, right, as well, because of chain rule. And exactly whether it's phi transpose or phi and so on, you will need to essentially reason it out with the matrices. But at least these intuitions give you like a way to verify whether this gradient term is reasonable. So we want the gradient to be 0 at essentially maximum likelihood, and here's what we get. Right. And then again, in matrix terms, what we do, we cannot directly divide phi transpose phi to the other side, but we can multiply the matrix inverse of this thing on both sides, and we get the maximum likelihood estimate of W. And again, you can use, I guess, reason about this phi transpose, which is m by n and phi transpose matrix is n by m, and the result of that is n by m, which is the size of W. And of course, you can multiply W with it. Let me see what happened. Okay, go back. So there's a question. Yes, phi means a basis function. My share screen turned itself off. Start it again. Right, why is this called the normal equation? I'll have to look it up and get back to you. Make a note of that. I'll reply in the thread afterwards. Okay, so it is one thing to, of course, obtain the normal equation. And it is another thing to, after doing this, convince yourself that it's reasonable, and then concurrently seeing, whether it's intuitive and how are the different estimates of the different components of the linear model plays out. This slide is used to convince ourselves of that. We wanted to know what the bias term really translates to, right, with these feature functions phi. So what we can do is essentially expand equation 3.15 and look at what its first component is. It turns out that it is, I'm not going to derive it in detail here. It's basically the mean of the target variable t minus the mean of the prediction function of each of the average of each feature functions. So, okay, let's go at that again. So the bias term, because it's fixed for any input, is basically the difference of the average of the target and the weighted combination of the average of the input. So that seems reasonable. And as hinted, and as you guys asked a little bit earlier, we can also obtain an estimate for beta with the phi terms involved. And if you care to double check with last Wednesday's note, it's basically replacing x with phi of x. So the precision parameter beta, the estimate for essentially the variance, sigma squared, is 1 over n, like the squared, the average square difference between the target and the prediction for all the data points. So here's another bit on the geometric intuition about what this normal equation is doing. So we copy the normal equation up here. And the prediction function, note that it's basically the sum over the weights times the basis functions. And it's basically an inner product of the weight vector and the basis or feature vector, right? So again, from linear algebra, as a reminder of linear algebra for some of you, if it's been a while, when something is written as like a linear combination of a bunch of feature functions or phis, we can think of these phis as a set of basis functions in high-dimensional space. And we can think of them as coordinate systems, right? And then y is basically like the w's are the coordinate values. So y, we can say that y lives in the space of these phis with the w as the coordinate values. These spaces don't have to be exactly orthogonal to each other, but y is still in the space of these phis. So T is, or the target that we're trying to fit, is not necessarily in the space of phis, because if the phis are too simple, for example, there are only linear functions, or like just linear plus quadratic, the true target might live in a more expressive or complex function space. So therefore, in this particular picture, T is drawn outside of this space spanned by these phi vectors. On the other hand, we also know that y is obtained as the least squares estimate, or maximum likelihood estimate in this case. Therefore, again, in Euclidean vector space, the least squares estimate of of some vector t, or basically the least squares projection of t into this space looks like this, right? So basically we can view y as the projection of t into the space spanned by phi. This is handy because look, x's can change, and then for the set of x's, t, yeah, you project t down to the basis spanned by phi x's, we get y. Okay, so this is a little bit involved, but I feel it's another way to obtain some intuition about what linear regression on basis are doing. Hope you find it useful. If my explanation didn't make sense, you can try others, such as ones on YouTube and so on. This material is covered by a lot of people. All right. So one thing that is worth noting is the normal equation is short to write, but it's not necessarily nice to compute, because if these phi's or phi transpose phi is not full rank, then taking the inverse is will have numerical nightmares. Right? It will not have a well-defined inverse that exists. On the other hand, the least square estimate of W still exists. So sometimes you don't want to directly compute this. Yeah, we won't go into length on this, but keep in mind whenever we do linear algebra for machine learning, there is an implication on numerical computation and how fast or how well behaved the result is, especially when it involves matrix inverses. For example, multidimensional Gaussians and this. And some of you may ask, if you have been just through a engineering linear algebra course, you may ask, what is yield conditioned? It's an intuitive, well, it's basically a way to quantify how close is a matrix to being singular. Okay, you said, you may ask, oh, what? Technically speaking, it's the ratio of the largest to the smallest eigenvalues. You can, there is the condition number of a matrix defined. I forgot which way around it is. But basically, if the smallest eigenvalue is too small, let's say 10 to the minus 15, that is not very good. Well, because this is a machine learning class in computer science, I need to, I think it's nice to discuss the computational complexity of computing these things as well. So basically, the cost of inverting a matrix of size m is roughly m cubed. What that means is, example, this, if I have lots of basis functions or my feature dimension is very, very high, inverting this is going to be hard or take a long while. With modern computers, you can invert a matrix of, I don't know, 10,000 by 10,000 on a normal computer, no problem. But more than that, it just slows down cubically. And that's a useful thing to know. And then the rest of the complexity comes from these matrix multiplies. I won't do that out in detail here, but I trust you to know in enough computer science to estimate in big O terms how much computation this takes. Right. And so basically the cost of computing this is related to the dimension of the weights and feature input, and also the number of data points. If both of them are big, then it's not so good. Well, if we have lots of data, all of you would have known from various versions of neural networks you encountered that you will never need all the data in memory. So the normal equation is what's called the batch form, right? So this 5 vector is basically all the data we have. It's n by m. That's a lot. We multiply it with itself and then invert it. So if I have millions of data points, I don't do this. What I do is this what's called sequential update or online algorithm. That again, right now is popularized by many deep learning packages. What we do essentially is still not far from the error function we looked at. So you basically do a weight update. The next weight is equal to this weight minus like some function of the error on let's say a particular the nth data point. So the extreme version of the online algorithm without mini batching that a lot of you now use is basically take one data point, update the weight slightly with it, and then just keep going, right? And this stochastic update scheme actually guarantees to converge to the same optimal, which is nice. It just does it very, like in each step, the update is very slight. And then the gradient here, because it's taken on one data point, it's noisy. But overall data points, multiple passes, randomized properly, these noise averages out. So this eta term is called learning rate. That a lot of you would have seen from neural networks. And this term, error term here, it's basically the sum of square errors, but just with one data point without the sum, right? And the phi x term is the same. So if you compare with the term a few slides ago, they are essentially the same, but just with one data point. All right, what we've done so far is to take you through the maximum likelihood estimate again with feature functions in matrix notation. And then we tries to look at the result in a few different ways in order to establish or convince ourselves that it's a reasonable thing to do, right? Or it's a reasonable result. We also talked a little bit about the numerical issues and complexity issues. So we're going to talk about two things next. How do we regularize? You must have also heard that term a lot. Let's look at how, what does it really mean, and bias variance. Okay, there are a few more questions. Okay, MLE. Yes, the normal equation is obtained without an iterative algorithm. It's just linear algebra. Okay, Fei Yang, thanks for looking up like how normal equation is defined. So great. Again, if you come from the big ML neural network realm, you would have seen this. I want an objective term, and then I have a regularized term that does not contain data, but only contains the weights. Right. So in, let's say, small ML, which is this class, you can also think about statistical ML as small ML. We look at what this means. A common term that, like in chapter 1 or last Wednesday, we basically said, well, how about we penalize the magnitude or L2 norm of W, which translates to this term. And we also impose the trade-off constant called lambda, which are hyperparameters. You ask, what does the normal equation look like if we do this? So it turns out it still looks like a normal equation. So you can, how this is derived is basically you differentiate this term. This is, let's say, log of the loss term with respect to W. You differentiate the whole loss term with respect to W, and then I get basically, well, lambda w in addition to the whole term. This is the MLE term or least squares term plus the lambda w. And then basically this term gets grouped into the term with w in here. I set the whole thing to 0, and the term involving lambda end up coming into this inverse. So what's the benefit of this, right? If we look at it from the linear algebra point of view, what this means is that this is actually a better conditioned matrix, where condition is in the sense that we talked about a few slides ago, meaning that in this particular expression, so lambda, phi transpose phi is a positive semi-definite matrix. So it can be singular, but it doesn't have negative eigenvalues. But the eigenvalue of this combination is actually lambda added to all of the eigenvalues in this phi transpose phi matrix. This is also in the matrix cookbook, right? So this means the eigenvalues, all of them is greater or equal to lambda, which is nice. There are also regularization terms that are commonly used that don't exactly regularize on the 2 norm or square norm of W, which is this circle picture. Well, you often see these contour shapes throughout machine learning and for the rest of this lecture. What this means is that basically all the W on this shape are treated the same by the regularizer, right? So if Q is less than 1, it's not a convex shape, it's a concave shape. If Q is equal to 1, it's a diamond shape. We'll talk about this a bit more later. And then if Q is greater than 1, it's a convex shape. The larger the Q is, the bigger the more bulged out the shape is. You can try and reason about what shape this is when Q goes to infinity, basically infinity norm. So in order to mathematically reason about this, let's take a brief detour in Lagrange multipliers. Because we were looking at, this is Appendix E talks about maximizing the function, which is equivalent to minimizing the minus of that function. It's a minimizing minus of f. So let's talk about maximizing the function on this page, right? We're talking about the objective f, and then we're talking about some constraint, g of x. So we're going to see Lagrange multiplier twice this semester. This is the first time. And then in the kernels, we're going to have another look that's slightly deeper. As a warm-up, so assume we wanted to maximize f of x subject to g of x as a constant or equal to 0, right? We can move the constant on the other side. Which will generate slightly different g of the same shape, right? So gx equals to 0 is represented as this arbitrary red line on the page. If we want to maximize the value of x on this red curve, it's equivalent to maximizing f of x plus lambda of g of x, where lambda is a little Lagrange multiplier, some unknown constant. Oh, well, this is easy to see because right, at least the objective value will remain the same because gx is 0 anyway on the curve, right? Moreover, at the maximum, the gradient of these two functions look like this. They are parallel or anti-parallel to each other, and they are perpendicular to or to the tangent of gx, or perpendicular to the curve at that point. To see this is that if the gradient of gx, if that's not perpendicular to the curve, then that's right, not the optimum point of the Lagrange multiplier. So it needs to move. And if the gradient of f of x is not parallel or anti-parallel to the curve, it will also need to move. Basically, there's a direction where it can move. It will improve the Lagrange, the value of the Lagrange. Again, these will take a little bit of time to sink in if it doesn't yet. Give yourself a bit of time. So moving on, how do we use this, right? So if we are to maximize a quadratic function in here, and subject to a constraint of the GS, which is the red straight line, then it basically, the optimum point should be a point where these things intersect, and the gradient of both functions are perpendicular to this GX, or this straight line. In this case, it's easy. It's where the straight line intersects, or well, cuts, just touches the circle, right? Okay. So what does this have to do with regularization? So here are the mental pictures for regularization for the linear regression we talked about. So the loss function are square errors. Therefore, their contour lines are, well, look like circles in the weight space. All right, and the regularizer, basically the penalizing term, W is the Q norm of W. When Q is 2 or square norm of W, they look like also concentric circles. When Q is 1, they look like diamond shaped, as we said earlier, right? So when Q is 1, this is the sum of absolute values of W, which translates to this diamond. You can verify sort of intuitively. So we know from the last page that the optimum happens when these two shapes are essentially tangent or just touching each other. So for a fixed, assume we know what the norm of the optimum W is. So basically we need to find a point where it touches the arrow function. And for L2 norm, it basically touches somewhere on the circle. For the same arrow function, the L1 norm touches it closer, or actually it tends to generate what's called a sparse W. Basically, more of the elements of W tend to be 0 because of the nature of the L1 norm being this somewhat pointy shape in the W space. Right. And this is essentially the motivation of lasso, like sparse linear regression, and a bunch of other things that names that this is known as. If you have taken like the statistics version of linear models or statistical learning, for example, the Tishby book talks quite a lot about lasso. This is roughly what it is. For multiple, if I have basically, what if my T vector is not like the training data is not a vector but a matrix? Basically, there are multiple targets that I'm trying to regress to. You can essentially do them independently. Also works out of the normal equation. I leave you to read the particular paragraph in the book. Okay, so we've spent an hour, and we nailed most of the technical content for this this session, and we have one left. So this one will take a little bit of a different thinking. Again, it might take a little bit of time to sink in, but I hope also after staying with me on like in real time or on video, you will at least go away with the intuition, and if the details don't sink in, try again. Okay, bias and variance. So these two terms are, I guess, very, like, they are popularly known, they are widely known about machine learning. Let's try and be a little more precise on what they mean, conditioned on the content of this lecture, right? So here is a popular picture, or one of the many pictures that depicts the intuition. In here, the center of the red circle is, for example, how we generated data, like the ground truth model, how data was inherently generated, what the ideal model is. The different dots, blue dots, are basically different fittings of the model, different attempts to get at the target, get at the true model from, let's say, different data sets, right? Like in theory, we could reason about if we had like many different random samples from this true model, how well we can approximate the target. So bias exists in the limit of infinitely many large samples from the data. It could be because that our model is not expressive enough, such as we are only fitting lines where the underlying data is generated by sinusoid. And variance exists. It could due to many things. It could be due to, right, the sample sizes are limited, and like many other factors. So bias and variance are just intuitively capturing all the different sources of discrepancy between what the estimate is and what the true underlying model is. And so what remains constant in this picture are the target, the true underlying model as well. The model specs, basically for fitting lines, then we're like for all of these blue dots were fitting lines. And also we assume that the learning algorithm is fixed. Because if we change learning algorithm, then the behavior of different dots will change. So what changes here are data subsets and the randomness in learning, including initialization, but can also include things like online learning, mini batches. Well, if you're doing essentially large neural nets, so everything else that's random that goes into your stochastic gradient descent. Okay, so here is the beginning of the math part. Let's again start from this familiar picture of, here's the function, target function y, which is parameterized by x and wave vector w, which is implicit on this slide. And the target, there is a, well, conditioned on y, the target, well, has a noise bump. Okay, thanks, Sai. Yes, I know this is fast. On the other hand, so I guess the overall objective of this class is that people expect to go through this semester and know, I guess, the foundations of key machine learning concepts. You will see these content again and again in quizzes, assignments, tutorials. A lot of tutors will start their tutorial by essentially going through the key points of the lecture content and points that people commonly find difficult. So those are opportunities to get a different explanation as well. So in the lecture, I'm afraid that giving, for example, 3 different explanations may not be the best use of everybody's like the lecture time as well. The other way you can you can also use our contact time, right? So post a question on Piazza or post a question here. If a lot of people have shared the same questions, I will try and address it in one of the future sessions or record a short video saying, right, this is where people commonly have questions, let's explain it. Or let's explain it with example and see if it helps. Yes, I know some people resonate with, yeah, things are going by in, like not in a slow pace. But I also know that it does get better through the semester. So just give yourself a bit of time, do your tutorial, talk to the tutors. Again, this SML is hard. I'm not going to exaggerate and say people, like most people, will be able to get it in real time. That's why I guess the 10 hours per week studying time is expected to go. All right. So in here, let's reason about the discrepancy between y, our estimate, and the true target, and break it down into several sources. And the next few slides are going to do this. I would say this next 3 slides may be the densest material in this class just yet. So let's do this. So we essentially we define a new notation, basically expectation of t, the target given x, which pretty much captures the intuition of y. Right, and note that this is right. It's integrated over the conditional probability of t given x. So it's a function of x, not t. And it's kind of hinted here, h of x. It's a function of x. So now we wanted, as hinted in the bullseye picture in the last page, we wanted to reason about the expectation of the square loss, which is the square loss is basically y of x minus t, and the expectation is taken over both x and t. Again, the expectation, even in this book, what expectation is taken over is often hidden and can be inferred. Doing so is important. So in order to think about this, we use a simple algebra trick. Basically, add and subtract a term in this quadratic term and then expand on it. So we add and subtract this new quantity that we just defined into this square loss. Okay, that's simple. And now we group the first 2 terms and group the last 2 terms. We expand this quadratic term expression. And it turns, well, so there are 2 square terms in the beginning and now we also end up with the cross term. All right. And the first of the, well, the cross term is 0 of it simply we just because we rewrote y of x as e of t, like as h of x. So the cross term is 0 when we integrate over x and t. But the 2 square terms are not. What this means is that if we look at E of L, we end up with this essentially 2 square error terms. The first term we will examine a bit more. The second term is h of x minus t. Basically, it's right. So if we remember in this picture, so h of x is, let's say, if we assume this distribution of t given input is and the prediction function is normal, then h of x minus h of x is this expectation, and then the target variable from last lecture, they were these circles that essentially has random noise, like generated by the true model and have random noise injected on it. So therefore, this is the noise term. The second term is a noise term. We just call it and then table it for now. Note that this particular equation appeared twice in different places in the book. So the first square error term does not have t in it because of the reason we said in 3.36. It's a function of x. T has been integrated out. The second term does have t in it, where 1.90 doesn't have t in it, which I would say correct that. All right. Just you might ask, yeah, why do we keep talking about square norms? Because square norms are nice. They are nice convex ball-shaped functions. We can talk about other norms as well, but the function shape in some cases will no longer be convex. Right? So these generalized, like Q not equal to 2 norms, they are called Minkowski distances. There's a picture in the book for it as well. So switching gears back to the square norm, we are going to decompose the first term into a bit more. And so here we are going to basically concentrate our energy on the first term, right? So we now introduce data D. We basically copy this E of L term 3.37 here. Each of the estimates Y depend on the underlying data set D, denoted as curly D. And we care about the square norm, square error between Y estimated from a particular data set and H of X, which, in here does not have an explicit dependency on D, right? And now we use the same trick to add and subtract a term, which is expectation of this Y term over different data sets D. So we know that for maximum likelihood, if we have infinite data, if we have infinite amount of data, the estimate agrees with the true estimate. So again, we expand these quadratic terms, the cross term vanishes because of this infinite data property. And because, right, we're taking the expectation over X, and this first term goes to 0. And we're left with 2 more square terms. One of it is basically the discrepancy of the estimation function Y over all different data sets with respect to H of X, basically the expectation of T given X. Right. The second one is the variance over different data sets between Y and estimate of Y over many different data sets. And these two terms are commonly referred to as bias and variance, or bias squared and variance, because the variance term looks like how the variance of a random variable is defined, but the bias term has the squared on the outside. Since we used this add and subtract trick twice, you may ask, how do you know to do this? It's going to be hard at the beginning, but basically you need to, the key is to come up with the term that will cancel with one of the terms in the cross term of the quadratic, and looking at the distributions. So this book, and for this purpose of this class, we're not going to ask you to come up with a new derivation involving bias and variance in this particular fashion, but we do expect you to know the decomposition and the intuition behind it. To summarize, what we just did is that we looked at the loss, square loss over regression terms, and decomposed it into 3 parts. The bias part is basically if I can get the best estimate of y from infinite data, how far it is from the true underlying model. And then the variance part is, well, what are the expected deviation of different estimates due to, let's say, different data sets and other sources of randomness in the algorithm. The noise part is, well, even when I know what the true model is, my observations are still not perfect. There can be observation noise. So the expected loss are essentially the joint forces of all these 3 forces. As we can see, if it's square error, all 3 terms are strictly positive. And now you might ask, okay, why are we talking about this? And what does it mean for linear models of regression? So let's look at this with the case of linear models with L2 regularization. In this case, polynomial kernels, I think sinusoidal data we were looking at on Wednesday. So if we set lambda to be high and fit, right now we can also sample random data sets and then fit different curves using the same regularization stress lambda. So if lambda is high, then in this case, the bias is high because, right, so what this also implies is the regularization strength, lambda, in L2 regularization implicitly controls the bias and variance trade-off. And this is how we use this in, let's say, linear regression. So the bias is high because the curves tend to be flat and they don't cover, they don't capture sufficient variations of the ground truth, the green curve. And the variance is low, right, in this top row. Right, and in this bottom row on the right, so the bias is low because it almost fits the green curve perfectly. And the variance is high, meaning across different random data sets, small data sets, the variations we get is quite big. In this case, right, the lambda, this lambda is really low. It's like the inverse or almost the inverse of the high lambda we get. And there are sweet spots in the middle, right? Where with this, in this particular case, lambda, log lambda is a negative small value. Remember the learning curve we talked about on Wednesday? Basically, the y-axis is some metric. in this case, square error. The x-axis is some controllable parameter for the learning, either log of lambda or the order of the polynomial, things like that. So, well, in most learning scenarios with real data, you will not be able to precisely decompose this error, like test set error, into bias, variance, and noise. But since these are for the synthetic data we generate, we can indeed do that and look at its effect with respect to lambda, right? So for, again, so recall the last page. For a high lambda, we have high bias, but low variance. The net effect of the combined bias and variance, bias squared plus variance, is still pretty high. And for a very low lambda, we have high variance and low bias, and the combined effect are still somewhat high. So this is, I would say this provides us a tool of thinking about and debugging, potentially debugging, coming up with hypotheses about how our models can be improved, right? So you could, I guess, ML practice 101 is you should try and do your hyperparameter search so that you get a ball shaped. Like if you see your, for example, performance test error keep rising or keep dropping, you might not be searching sufficiently on one side. And then once you get to that, then you can reason about which side has high bias and which side possibly have high variance, and see if you can do something to improve that. I know hyperparameter search is sort of seen as a black art in a lot of machine learning practice, but looking at it this way will give you essentially an applicable weapon to analyze what your performance is and come up with principled improvements rather than random guess, like just searching in the dark. We talked about unbiased estimates, but since we're talking about bias, I might just like hone in this point a little more. Basically, the word bias does not carry a negative connotation, right? So, well, I think whoever coined, like named this thing bias, preconditioned people into the psychosemantic trap of bias being bad. So the more proper technical name could be, the component of error that's orthogonal to the variance. Right, so it's one of the components of error. And if you come from statistics, why guarantee zero bias if you can trade it off with other errors? Oh, yes, unbiased estimator may be good in one hand, but they may or may not be good on the other dimensions. So this, I think, is an intuitive summary of what we said. Like in this decomposition, so we can trade off bias and variance. The noise can come from the data observations and cannot be removed from the expected loss. So there is a limit on what the loss should be, and it's usually not zero. Again, in the very over-parameterized cases like large neural networks, there are strange observations that we will probably have time to talk about in the generalization nature. So to properly analyze the variance decomposition, so we at least need many data sets. It's not always possible. Ideally, we also like to know the underlying true model, which is also not possible for many practical tasks. So, okay, I'm going to okay. Right, so there was a question on the learning curves and bias variance decomposition. I believe it's been addressed. Yes, okay, great. So I would like to spend the next few minutes talking about like the modern development in this space. In particular, I would preface by saying that, right, so there's a lot of talks about explainable models and interpretable models and making machine learning more usable and transparent and so on. These are not entirely new discussions, so I would want to remind people that, well, machine learning didn't just happen in the last 10 years. There has been lots of great work in statistics optimization and machine learning before that. Case in point for this particular thing is that Robin Dawes, psychologist actually, famously noted that what he calls improper linear models, basically unweighted linear combinations of a bunch of factors, are good for deciding, like perform surprisingly well for predicting many real world outcomes. In the paper and the commentary around it, there is also a famous example of this kind on predicting like the failure of a relationship or a marriage. You can look it up. I'm not going to spoil it for you. It only has 2 factors, but worked really well. So here's the modern development. I'm mainly talking about work led by Cynthia Rudin. She is a professor at Duke University. She just won the prize for what's called the Squirrel Prize in AI for Humanity. So this is a very new prize, but it's pitched as the equivalent of the Nobel Prize for science in general and Turing Award for computing. It carries $1 million US dollar prize money. So she won this for her work on sparse linear models and many other related work. We'll talk about this in a little bit in her own slides. And also she's written a perspective on this in Nature of Machine Intelligence a little while ago. So she won this award for pioneering scientific work in the area of interpretable and transparent AI systems in real-world deployment. The advocacy of these features in highly sensitive areas such as social justice and medical diagnosis, and serving as a role model for researchers. You can read and watch more of her work there. So in like less than 5 minutes, I'm going to talk to you about what interpretable models are. They obey a domain-specific set of constraints that makes it computationally easier to understand. Not necessarily like have less error, but hopefully also performs well, but the more emphasis is on easy to understand. So they should be useful to someone or obey structural knowledge of the domain. There's a whole, I guess, spectrum of how you design these models. We started with medical diagnosis in the beginning of this lecture, so let's just look at one of Cynthia's models for this. Right, so her model is called 2Help S2B for diagnosing brain conditions in patients. Right, and it has 6 factors extracted from hundreds more that are measurable from patients. And so doctors can apply it in the same manner as the APGAR score we talked about earlier. And depending on score, there's a assigned calibrated risk value statistically. And moreover, doctors do not simply apply these models, right? So I would personally argue that the job of doctors is one of the last to be replaced to be machine learning, if ever, because diagnosing a patient is so complex, right? So they would taking into account the rest of basically the co-occurring health conditions that are there and history, health history, and the possibility for different kinds of treatment, right? So to diagnose properly, right, doctors can calibrate these scores with information that are not recorded in the database. So how is this model derived? It's called basically, it's done in a 2019 paper by Cynthia and his then student Hudson, now also a faculty member at UC San Diego. So they call it SLIM, super sparse linear integer models that are risk calibrated. What this correspond to is similar to what we saw, right? A logistic loss term for classification, in this case, not exactly for regression, and also a regularization term which has zero norm, which is even sparser than the one norm normalizer. Moreover, they want these lambdas, these are the weights, to be small integer coefficients that are ideally co-prime with each other. So which means these lambda can only take integer values. So this objective, if solved properly, will produce a sparse linear model with integer coefficients that people can apply, which is nice. The computational approach that gives us the optimal lambdas, on the other hand, it's not so easy, right? So it's what's called a mixed integer nonlinear program. If you want to learn more about how this kind of program is solved, take the optimization class in semester 2. If you know how practically you can do this, if you are presented with one of these problems, use this software called Gurobi, which have many of the functionalities built in. Okay, so how does this do, right? So this particular model is validated on independent patient cohorts of more than 2,000 and is implemented in multiple large hospitals in the US with an estimated savings of 6.1 million. And because of this, they can also monitor and serve more patients. All right, so that's all. We are like at the point, a little over one and a half hours. We've talked to you about linear models. We rederived maximum likelihood in matrix notation and showed how it connects to least squares. We talked about regularization, bias variance for linear models, and we looked at interpretable models as a modern development in this area. Okay, I know this this will feel a bit dense, so yes, do ask a lot of questions on Piazza with tutors, and I'm also going to stay on for like if you have questions right now. I'm also happy to go back to some of the chunks of material and use the next 25 minutes or so to go through them again if you think you would like me to do that. While people are thinking about questions, I'm just gonna try and tell Teams to stop the recording.